This is a brief discussion of what we mean by linearly independent vectors and what the properties of linearly independent vectors are. What I'm using as a definition is to say two vectors are linearly independent if they are not scalar multiples. They're not scalar multiples of each other. So I'm going to underline not. Okay. Geometrically, all that means is that the two vectors do not lie on the same line through the origin. So here's a vector. Here's a vector that goes through the point 2, 1. Here we are at well, I can't write 2, 1 so easily, but here we are. We've gone over 2 in the x direction and up 1 in the y direction. This is 2, 1. The vector, so let me write that. So here's 2, 1. And I would argue that the vector 4, 2 is not linearly independent because 2 times 2, 1 gives me 4, 2. So these two vectors are scalar multiples of each other. 4, 2 is a scalar multiple of 2, 1. Geometrically, if I were to draw 4, 2, it would look like this. I would start at the origin and I would go out 4 units and I would come up 2 units, and you see what I mean, that they lie in the same line. Even if I went in the opposite direction, even if I looked at the vector, let's say minus 6, 3, so, well, you get the point, okay? As opposed to a vector that does not lie in this line, so for example, the vector 1, 3. So there's no constant that I can multiply 2, 1 by to get to the vector 1, 3 for all k. Okay. So here I am at 1, 3. Here I was at 2, 1. And clearly, those two vectors are not scalar multiples of each other. They do not lie in the same line. Therefore, we say that those two vectors are linearly independent. Okay, that's the first thing. So then there's a theorem that says if two vectors are linearly independent, so we've got two linearly independent vectors in the plane, given any vector, any other vector in the plane, there will exist scalars k1 and k2 so that a linear combination k1 times x1, y1 plus k2 times x2, y2 will equal x0, y0 for any vector I choose in the plane. What this is saying is that from two linearly independent vectors, so here are two linearly independent vectors, they do not lie in the same line, I can build any other vector. I'm going to try to draw a straight line, not so good, but I can get to any other place, and it doesn't seem that obvious at first, but here would be one approach. If I were to multiply the vector x1, y1 by a negative number and stretch it a bit, I could, by multiplying it by a negative number, I could move in this direction. And then, so roughly, let's say I multiply it by some negative number, and I stay on the same line, but I move it in the opposite direction. So here's a vector. Multiplying it by a negative number, let's say -2 perhaps, might get me to here. It would move me in the same direction, but to here. Then, using this direction, you can see, if I were to stretch it, I can get up to x0, y0. So I'll draw that also in red. And so I would argue that this vector is some stretching k1 of x1, y1. This vector is some stretching, I'll call it k2 of x2, y2. And as I've already shown in class, and you should be familiar with vector addition, the way we add two vectors is we start at the origin, we draw the first vector, we take the second vector, we put it at the head of the first vector, and we draw it, and their sum starts at the origin and goes to the head of the second vector and gets us anywhere we want. Let me show you an example. So here are two linearly independent vectors, 1, 0 and -1, 2. 1, 0 is here, -1, 2 is here. Clearly they're not scalar multiples of each other. I'm being asked to get to the point 2 minus 3. So here's 2 minus 3 in quadrant 4. How is it possible? Well, what I expect, so first I'm going to make a little drawing. What I expect I'm going to need is I'm going to take -1, 2, which does not point in the right direction, but if I multiply it by a negative number, it will be moving in this direction. And so I'll find some negative number to multiply it by, and then when it's lined up at the height of -3, I'll add to it some scalar multiple of 1, 0, and it'll bring me across right to the vector 2 minus 3. So I'm expecting just from this diagram, and I'm going to solve and find out exactly what k1 and k2 are, but I'm expecting to find that k2 would be a negative number bigger than 1, because it looks as if I'm going to need to stretch -1, 2 by a certain amount. But k1 looks like it'll be a positive number because it's moving in the same direction as 1, 0, but it looks a little shorter than 1, 0, so I expect that'll be some fraction, something less than 1. Let's go ahead and do the math and find out. So I'm going to create a new page, if I can. Maybe I can't. Yes. And so here's our problem. I'm going to find a k1 times a 1, 0, and a k2 times a -1, 2 that will build for me 2 minus 3. So previously I was looking at the geometric picture. Here's strictly the algebraic picture. This will be true if k1, so this is, I'll do it in 2 steps, multiplying through by that scalar, I have minus k2 and a 2k2. Two minus 3. Adding component-wise, this will be true if k1 minus k2 is equal to a 2. So first I'll even leave it in its vector form. And 0 plus 2 k2 will equal minus 3. Well, this gives us 2 equations and 2 unknowns. It says this will be true if k1 minus k2 is equal to a 2, and if 2k2 is equal to a minus 3, well, this implies that K2, let me erase that K2 is, as predicted, a negative number, in fact, negative 3/2, so that makes sense. And if I plug in K2 into this equation, I will have the statement that K1 minus 3/2 has to be a 2. It isn't hard for us to see. That's K1 plus 3/2 is equal to a 2. K1 is going to have to be a half, as predicted from the previous picture. Unfortunately, I'm not able to scroll back and show you, but you can play this again and you can rewind this and you can see that in the previous slide I was showing you that sure enough K1 would be some fractional positive number, K2 would be some negative number bigger than 1. And so this is just a verification for this one example that given two linearly independent vectors, I can build any vector in the plane, and you could try other examples, see how you would get to 7, 9, or any other place. You'll be able to find a K1 and a K2 that stretch these two vectors and perhaps change their direction so that when you add them together, you get whatever vector you're after. And that is the great power of working with linearly independent vectors. And that's it. Thank you very much.